Right, let's start. So this is your wave nature of particles. We started this topic last class, and I gave you some brief idea about it. So ওইটা হচ্ছে এই পার্টটা, the last part here. They understand the de Broglie wavelength as a wavelength associated with moving particles. Use lambda equals to h by p. Describe and interpret qualitatively the evidence provided by electron diffraction for wave nature of particles. So 18টা point হচ্ছে cover course. I'll just go through it one more time. Recap. Ajke we're going to start the core topic. It's called the photoelectric effect. Okay, so that's what we'll be doing next. Right, so what is this topic about? So here what we did was an experiment. Let me just go through the whole thing, okay? So the experiment was we took an electron gun. What does an electron gun do? It fires electrons, right? Do you remember the name of the process that causes electrons to be emitted? No. There was a particular way by which electrons are emitted from a material if you heat it. No, velocity selector is the one that sets the velocity. What is the thing that causes electrons to be emitted from something? You're right. That's one of the ways. That's radioactive decay, right? But how can I willingly make something release electrons? Because radioactive decay is random.
Energize?
How?
Ionize?
Okay, very close. So I think the IGCSE students, right? GC chilo O level. It was called thermionic emission. So thermionic emission was basically a coil যদি থাকে ওই কয়েলটাকে যদি অনেক হিট আপ করে এখান থেকে কি বের হওয়া স্টার্ট হয় electrons. এটা একটা চ্যাপ্টার ছিল the working of a oscilloscope. ওইখানে পার্ট ছিল, not important for us. The idea right now is that what is being fired from this thing? Electrons. And what did we anticipate originally? Originally we thought that if there was just electrons fired, right? So let's say we're just firing electrons straight at the screen. Our original anticipation was that on the screen you'd see what? Just a dot. A dot যেটা show করে যে what hit the screen, electrons, right? But things changed, once we fired electrons at this salt crystal, we found this very unique pattern forming here, and that pattern turns out is a diffraction pattern, and a diffraction pattern consists of maximas and minimas, right? Diffraction pattern is an exclusive property of what out there, waves, right? So suddenly you have like a wave forming on the screen. There's absolutely no waves involved here, that's proven, but something happens inside that causes the electron to turn itself into what? A wave, right? And that's when we realize that every particle, this part is very important, okay? Every particle with momentum has a wavelength. So when you're moving, right, you have a wavelength. Anything that's in motion has a wavelength, okay? That is the fact. So there's nothing, there's no exception to this case. So anything that's moving has a wavelength. If I throw a ball right now, it has a wavelength, right? But it also has momentum. And wavelength and momentum are a little contradictory to each other. Momentum is a mechanical feature. It's what gives the objects the mechanics. Momentum, right? And wavelength is something that gives it wave properties. They're two different sides of a coin, right? So the thing is that when you have a ball thrown, right, it has wavelength, it has momentum. What does it show to you? That's important. So the thing that we found is that when you throw a ball, right, the ball has mass, the ball has velocity, which means the ball has what? Momentum, right? It will show mechanics related features, like all the mechanics related features. What are mechanics related features? Force, acceleration, pressure, change in momentum, all these features, right? But if you give this ball an opportunity to diffract, what would that opportunity have to be? It needs to interact with a gap that is what to its wavelength, similar to its wavelength. This ball will then interact with the gap and lose all its mechanical properties or particle properties. And what does it become? A wave. So it shows that the wave behavior was always there. It only shows the wave behavior when you give it the opportunity. This concept is called the wave particle duality. So what's wave particle duality? That everything out there, right, has a wave behavior and a particle behavior. So is the reverse true, that a wave also has momentum? Yes. Okay. So wave particle duality states that you have your particle on this side. This is a particle, right? And as it crosses the gap, what does it become? Wave. So it means that this particle that you see here had two features. What are the two features? Momentum and wavelength. And somebody actually brought them together to get this equation out there, arguably one of the most important equations of quantum mechanics, lambda equals to h divided by p. Why is this equation very important? It allows you to convert something with momentum to what? Wavelength, and something with wavelength to what? Momentum. This is that equation that joins the two different branches of physics. It takes the particle behavior and wave behavior and puts it in one equation, right? So this is called wave nature of particles. So this proves that particles can turn into waves. Okay, that's it. And this is just that much that you need to learn. You need to learn this equation. It's called the de Broglie wavelength. Lambda equals to h by p. H is the Planck constant. That's the value out there. And for diffraction to take place, your gap has to be either equal or what than the wavelength, less than the wavelength, right? And that's when we found that if you try to find the wavelength needed for a person to diffract, right, the gap that you need is that this gap doesn't exist in the universe, okay? So that's the reason why a person won't be able to diffract. But if you look at a mass of an electron, the speed of the electron, lucky for us, if you put the mass and the speed of the electron, you get this value, which, by the way, is very commonly available in nature, in like crystals and other places. So yeah, that's the reason why an electron can diffract, but nothing else can diffract. So if you want to diffract anything else, you need a very small gap, and the very small gap doesn't exist. Okay, like it just doesn't happen naturally. If you artificially can create it, it will actually happen. Okay, but you know, they artificially create for a scope 9. So yeah, that is the wave particle duality. Do you have any questions? Let me clarify, because এখন যে টপিকটা স্টার্ট করব has nothing to do with what we did. Okay, so this is just this. So this is just an evidence that wave particles can show what properties? Wave properties. Okay, so that's just it. So bolo question থাকলে from previous class, if you have any confusion, doubts that you need to clarify. Right. So the most common question is that they'll ask you, they'll give you some properties of a particle, and they'll ask you, what is this wavelength? And then they'll ask you, if it passes through a certain gap, will it diffract or not? This is one of the types of questions. The other one is that the more common one, 3-mark question. Give evidence that a particle has wave properties. What would that be? Yeah. So you just say that we take an electron, which is purely a particle. It has mass, it has momentum, it has velocity. We fire the electron at a salt crystal. As it passes through the salt crystal, on the other side, we do not find the electron anymore. What do we find from it? Diffraction pattern. And diffraction can only be executed by what? Waves. So it just shows that the particle turned itself into what? Wave. Now then there can be a follow-up question, why? And what's the answer? Why did the electron turn into a wave? Correct. That's it. Okay, so it passed through a gap similar to its de Broglie wavelength, right? So the de Broglie wavelength is basically a hidden wavelength for every matter out there. If a gap exists that matches the de Broglie wavelength, that matter won't be a matter anymore. It turns into what? Waves. Okay. Clear? Anything else? Yes. Right. So this is called wave particle duality. And in wave particle duality, we learned that if you take a particle, like an electron, right? And if you fire the electron into a salt crystal here, this is a salt crystal, the electron, which is a particle, enters the salt crystal, right? But as it comes out from the other side, the electron is not there anymore. You see this pattern formed here. This pattern is actually your diffraction pattern. Now, what undergoes diffraction? Waves, right? So, but you didn't send any wave. What did you send? Particle, right? So where did the wave come from? So the answer is that the particle turned itself into a wave. Why did it turn itself into a wave? Because every particle out there, right, has a wavelength. It's hidden property. Okay, anything that's moving has a wavelength. A car has a wavelength. If you're walking, you have a wavelength. A ball has a wavelength. So the electron also has a wavelength. And as the electron went through this crystal here, it found a gap equal to its wavelength. And whenever you have a gap equal to your wavelength, what do? You diffract, right? So that's why it diffracts. So this is evidence of wave behavior of particles. Okay. No, it was just a coincidence. So when they were experimenting this, their expectation was that they'll fire particles. It will form this on the screen. It'll form a line that looks like that. These are the places where the electrons hit the screen, and the gaps are the places where the ions were. So it's like, imagine I have like a wall here, like this, and there are like gaps in the wall like that. Okay, and what I do is I fire paintball at the wall. Do you know what paintballs are? And you'll find that paintballs are hitting here, there, everywhere. But you'll find that there are paintballs in this place on the wall and paintballs in this place on the wall, right? Wouldn't that tell you that the structure of the wall in the front is of what shape? We anticipated this, that we'll fire millions of electrons out there. They'll create this pattern out there. That pattern is the place where the electrons went through. The rest of the pattern is the place where the ions are, and you know how the ions form, right? But once we did the experiment, it never gave a pattern. It rather gave a diffraction pattern. And from there, we understood that the electron turned into a wave. Not a problem for us, because the diffraction pattern then can be reverse engineered to find out what the structure of the atoms are. Because diffraction is caused due to slit size. So this pattern must have been generated by something that looked like that. That's how we know like this exists. Wavelength of? Oh, they didn't measure it. I calculated it. This is the formula. So this was a theory. It was never proven. No. Now we know. Now with this we know. But before this experiment, it was just there that waves and particles are like, the two sides of a coin. But then this proved that it is actually true. Okay, so this is it. This is not the famous experiment though. That is the one. That is the experiment that changed physics. Both. Last class or target class? Yeah. What is last week? Wednesday. Wednesday the course per class course. Yes, and also Saturday. Saturday we went through the example here. Just went through the whole thing one more time. Right, let's move on. So এখন যেটা করব এটা হচ্ছে the photoelectric effect. আচ্ছা, একটু শুনো। কিছু লেখা না, it's very elaborate. It's one experiment that I'll be explaining, nothing else. Okay, and that experiment is the chapter, so you can understand the detail that you need to look into. But it's a parlay. It's, I think, one of the easiest 12-10 marks in your paper. This is almost there every year. Quantum physics থেকে একটা question আসে, and it's mostly photoelectric effect. Okay, and then there's nothing they can change about this topic, because it's literally an experiment that they're giving you, right? There's no variation out there. So এটা যদি বুঝো, এই সেম জিনিসই বারবার জিজ্ঞেস করবে. There's no scope of variation in this chapter. Okay, so দেখি কি হচ্ছে এখানে. So what is this photoelectric effect? So before that, let's get back to the experiment first. So experiment premise টা তোমাদেরকে বুঝাই. So the person doing this experiment, right? Tar aim ki chilo? What was he trying to do? So he has heard of the fact that if you shine light, right, light carries energy. That's been proven. I'm talking about 1800s that light actually carries energy. That has been proven, right? And he also has heard that if you give energy to electrons, what would the electrons do? They will come out of the atom. So these are two ideas that he knew, that okay, wait, light carries energy and electrons can leave the atom if you provide them what? Energy. So his aim was to beam light onto a material, enough light. So what does the material start to release? Electrons. That was the aim. Okay, so ওটা করার জন্য কি করতে হবে ওটা আগে আমরা বুঝি. So what he did was, he took a metal here, he took zinc. So zinc একটা sheet নিছে and he connected the zinc sheet. The original version is a little complicated, I'm just বলে রাখি, but আমি একটু modify করবো. He connected it to something that is long now not part of our syllabus, a gold leaf electroscope. Do you know what a gold leaf electroscope is? So gold leaf electroscope is a device, right, that tells you the presence of charge. দুইটা leaf থাকে, as charges are excess or less, right, the leaves diverge and converge, right? So the original thing was this. You have to understand this is late 1800s, 1900s. তখন কোনো রকম fancy device ছিল না. So charge বের করে একটাই way ছিল, a gold leaf electroscope. And gold leaf electroscope didn't tell you the charge amount. It only told you what? The presence of charge. So আমরা এটাকে modify করে, we'll connect this to a device that will tell you the charge and everything. It's called a coulomb meter. So coulomb meter হচ্ছে একটা ডিভাইস যেখানে হচ্ছে তোমার চার্জ যদি থাকে তাহলে tell you what the amount of charge is. Does that make sense to you guys? So we'll just make a modification here, which means if this is neutral, the reading here would be what? 0. If this became positive, then this would become positive একটা value দিবে, এটা negative হয়ে গেলে এটা negative দিবে. That's what the coulomb meter does. Now the person wanted to test what? If I shine light on this metal, will electrons come out or not? Can you tell me if electrons did actually come out from this metal? Like if the person was successful, right? What reading would this give you? Positive, yes. So his anticipation was to get a positive reading. Positive telling you that the electrons have left the metal, right? So what did he decide? So he decided to take a light source, and light source will come precisely describe because light source is the problem to arise of it. So he took a light source here of red light. Okay, so let's write down all the properties of the red light here. So this is red light. And do you know what the wavelength of red light is? 6? Yes, 700, the Korea, 700 is also acceptable. So 700 nanometer, that's the red light wavelength, okay? And there's another thing that you need to watch out for, the watt of the light. Intensity. The intensity here is 100 watt per meter square. So you have a red light of 700 nanometer, intensity 100 watt per meter square. 100 watt per meter square intensity kerokom? It's like a lamp brightness. Okay, LED though, they're much more brighter. They use like filament lamp back in the day with a filter, which power on it, brightness on it. But not our point. The point is 100 watt per meter square, something like this. This is going to be important for you later on, okay? So he took this light source and he shone the light on the metal. So you can light bear, it clearly falls on the metal here. And what does light carry? Energy. Literally, the definition of light is a wave, and a wave is a thing that carries what? Energy, right? Turns out, as he did this experiment, there's nothing happening here. Tomar red light use kortese, tomar kono plus minus zero hoyese, which is fine. I mean, it could mean that the energy you're providing is what? Not strong enough, right? What would you do? Can you tell me what can you do here to provide more energy? Yes, intensity definition কি আমাকে reminder দিবা that তোমাদের জানতে better হবে. What is the definition of intensity? Power per unit area. So আমি যদি intensity বাড়াই, am I not literally increasing the energy, right? So yeah, the person went and bought, like, let's say, a powerful lamp and made this 400 watts. 400 watts, by the way, very bright. Okay, 400 watts হচ্ছে বাসে কোন use করা যাবে. It's one of those lamps, gari headlight. So if you look in a car headlight, day brightness, that's 400, right? So ওইটার জন্য the power here is going to be what? Much brighter একটা light দিবে, very intense light. And that red color light fell on this thing, and surprisingly, nothing. Okay, so something strange is happening. Tomar electron, for whatever reason, lighter kaছ থেকে energy নিতে চায় না. Now to test this hypothesis, the energy actually আসতেছে নাকি, the person actually looked at the temperature of the surface here, and the temperature of the surface here was very high, like it's hot to touch, which means there's a lot of energy out there, but electron বের হচ্ছে না. Whereas we learned previously, electron behavior. That's how you can remove electrons, right? How? By rubbing and friction. That's very limited amount of energy, right? You're providing 400 watt per meter square, and electron ekhno ber hocche na. So there's something going on here. Like the electrons were hesitant to interact with what? Light, right? Acha. So the person didn't go here, but we'll go here. Amra jeta korbo, we'll replace the lamp with a lamp that is so bright that eta jodi hocche, if a person looks at it straight away, like, instant blindness. Okay, so just for the sake of it, let's go to the extreme. 40,000 watt per meter square. It's a small star, you could say. Okay, it's very bright. So এটা যদি দেওয়া হয় কি হবে? You'll have insane amounts of light here. In fact, so much light that the metal might even start to melt. It'll be that hot, right? But still no electrons. So something is happening here. Electrons berote যাচ্ছে না. The electrons just don't want to interact with light. And make it. Oh, we can try that. Okay, we'll try that later. We'll not just increase the brightness. By the way, blue would change energy? No, right? So if I give you a lamp, 100 watt, and I give you a lamp, blue color, 10 watt, which one is more powerful? Red 100 watt or blue 10 watt? Yeah, so the blue shouldn't be an issue, right? It's the power that matters. Okay, so if I use blue here, I mean, she could be right. So so far একটা জিনিস just establish করে রাখি, it's not working. এখানে light দিয়ে emission করা যাচ্ছে না. Are you with me so far? আচ্ছা, এখন I'll take her advice. So she wants to change the color of the lamp, right? The color change হলে কি হয়? We'll try everything. So আমরা এখানে we'll repeat the same thing, and this time instead of a red color light, let's use blue. So blue color light use great. And do you know what the wavelength of blue is? Yeah, 400. Violet is 400, but we'll just put blue here, 400 nanometer, and we'll use blue color at the lamp এখানে, and blue color light এখানে পড়বে. Now it's just changing the color. Did I change the intensity of my light? No, right? Which means my lamp is still providing how much energy every meter square? 100. So it's not a powerful lamp or anything, right? Blue dilam ekhane. And now electrons are emitted. Yes. So somehow blue color, the zinc here interacts with. So the strange behavior here is that light, energy, right, and electrons are related to somehow with colors, which doesn't really make sense because our 100 watt, 400 watt, 40,000 watt, that's energy. Color to কোনো factor নেই এখানে. So why is blue color allowing emission? So এটা যখন first course the person didn't use blue actually. The person used ultraviolet. So he went from red, green, blue, tar metal blue te hocchilo na. So he went to ultraviolet, and he went to ultraviolet and emission started. And he named his paper, it was like a thesis he was doing, the ultraviolet catastrophe. Because out of nowhere, ultraviolet the kaaj korche. And the reason why I called it a catastrophe, I'll tell you why. Eta to thik ache. You know what he went on to do? He took his light here, blue color dhorlam, and he put this power to 1 watt per meter square. 1 watt per meter square is so dim, right? Our eyes can't pick it up. Yet, what came out from here? Electrons. So somehow electrons are, interacting with the color of the light. They don't really care what of the light, energy of the light. Do you see what's happening here? So আমরা যখন কালারটা চেঞ্জ করি তখন emission হয়. There's nothing to do with the energy here, which completely contradicts the whole idea, because what do you need to provide to the electrons for emission? Energy, right? So এখানে color cannot matter করতেছে. And yeah, this thing was the ultraviolet catastrophe. So does it have to do with the wavelength? Yeah. So something has to do with the color of the light. How is color related to energy? So it turns out there is no relationship between color and energy. If you take light as a wave, so if you consider light as a wave, right, color and energy has absolutely no link. But if you consider light to be a particle, things change. Why? Because in 1912, Einstein came up with the equation for a very random purpose. Purpose. He said that energy of a light is given by this formula here, E equals to HF. And he said that the energy of a light actually depended on the watt of the light, the frequency of the light, not the watt of the light, the power of the light. Why did he go into the realm of, let's say, wave and particles? He came up with this equation to describe something else, his theory of relativity, where you had to explain. So theory of relativity is this thing about gravity and everything, where in order to explain behavior, you have to consider light to be a what? Particle. And he said that light was a particle. No proof, nothing, just a math. And so that's it. It's wife actually did it. So he came up with a paper, and he said that the particles, he called them photons, right? Ball actor. ওই বলটা was what carried the energy, not a wave. And this is contradictory because আমরা একটু আগে গিয়ে হচ্ছিল proof করলাম it's a wave diffract করে and সবকিছু করে, right? So he said that the energy of a photon was the term he provided this. He said that this is a quanta মানে হচ্ছে, that's where quantum physics come from. Quantum means packets. This is a Latin word for packets. Okay, so he said that light, it came in packets, not in a form of a flow. So if you were to carry light from one source to another, instead of a pipe carrying water, what was the way water was carried? In small glasses. So, fixed packets se jeto, tapo pani theke pour kora. That's Einstein's version, right? No proof, nothing. He just said this, right? And then, eventually this catastrophe proved it. Why? While doing this experiment, we found that the frequency of light is actually related to what? The energy it provided. And the energy it provided increases what increase? Frequency. So এখানে যেটা হচ্ছিল, red light is actually low frequency. The red light photons did not have what? Enough energy. But once you turn them into blue color light, what happened to their frequency? It increased. So what happens to their energy? It increased. And that's the emission took place. Yes.
What about wave that decrease for? So how is it not related to wave that accelerated?
No. Wavelength is the problem. But wavelength is a dependent variable. Can you change wavelength? No, you can't. You can only change what? Frequency and speed, which changes what? Wavelength. That's why frequency is the determining factor here. So yeah, the thing is that this is the formula to use here. But what is the overall outcome of this whole experiment? The overall outcome of this experiment is, for the first time and the only time, we have evidence that light behaves as what? Particles. Okay, একটু আগে আমরা যে এক্সপেরিমেন্টটা করে আসলাম, which was opposite. কি ছিল এটা? Particle behaving as a wave. That's the electron diffraction, right? This experiment proves waves can also behave as what? Particles. And this experiment is called the photoelectric effect. You are emitting electrons using what? Light. That's why it's called the photoelectric emission. And this is the evidence of the particle's nature of light. And then we eventually find that this equation is true. And yeah, Einstein, despite all his equations and math and theories, he got Nobel Prize only for this one, not for the others. Okay. Yeah, so it's like a very fringe idea of his, which was not even his real aim, but this is the thing. So he was the first person to properly suggest that light is a packet and particle, and then this equation and this experiment proved it. Energy. So not continuous energy, it's just bunches of energy. Planck constant. So H is we argued data 6.63 into 10 to the power minus 34 joule second. So if you put a frequency of light here and the Planck constant here, you'll find how much energy every photon has. Okay. So yeah, this is the photoelectric effect. আমাকে questions থাকলে বলো, let me clarify. I'll give you notes on these. কোনটা? Oh, so the zinc, it's a metal.
Like, why are we using that?
Oh, we want to emit electrons from it. So একটা কিছু তো use করতে হবে. The person chose zinc.
Because
Random.
iron, copper.
Everything, any metal use করতে হবে. What metal হতে হবে? So the photoelectric effect definition হচ্ছে the removal of an electron from a metallic surface using light. Non-metal হয় না এটা.
What's that for?
So the original device that detected it was called the gold-leaf electroscope, but since we don't have that in the syllabus and no one uses it anymore, we directly use a Coulomb meter here, and it directly tells you charge আসে নাকি যায়. Wave থেকে না আমরা ইলেকট্রনকে বের করতে যাচ্ছি from the metal using light. হ্যাঁ ওটা আরেকটা এক্সপেরিমেন্ট. না wave কে particle বানাতে যাচ্ছি, electron না. So the previous was not electron, previous ছিল particle কে কিসে কনভার্ট করছি, আর এখানে কি করতে যাচ্ছি? হ্যাঁ এখানে particle হয়ে যায়. It becomes a particle. ওইটাই এখন বুঝাবো. আচ্ছা, so what is actually happening here? So let me clarify what is going on here. So it's a strange realm of quantum physics, but bear with me. So when photoelectric effect is not taking place, right? এখান থেকে তুমি যদি observe করো দেখবা কি বের হচ্ছে waves. Like somehow you could see waves, right? You'd actually see waves coming out. So let's say you use red light here, দেখবা যে waves বের হচ্ছে, photoelectric effect হচ্ছে না, waves বের হচ্ছে. Somehow the moment you have photoelectric effect taking place, you'll start to notice এখান থেকে আর কি বের হয় না wave, rather কি বের হচ্ছে small particles of light called photons. And this is very strange. I'll tell you why. It's the light source knows the target. It's a very strange branch of physics. Let me tell you key hoy. So apparently the lamp, when it releases the light, releases it as a photon. If it knows that the photon will go and interact with what? A metal. It will be metal সাথে interact না করে, what will it release that as? Wave, right? Now the strange part here is that you can't fool it. So let's say তুমি হচ্ছে কি করলে একটা প্লাস্টিক রাখলা সামনে, এখন কি বের হচ্ছে wave, right? তুমি wave বের হচ্ছে সাথে সাথে কি করলা metal দিয়ে আবার প্লাস্টিক প্যাক করলা. So you want to fool it to create some photons, right? No, it'll still be a wave. But the moment you place something here such that it hits the metal, দেখবা কি বের হচ্ছে photon. So there's no way to trick it. যে wave বের হচ্ছে and you entice it by giving a plastic. Yeah, wave আসতেছে, right? And wave আসতেছে, you put the metal out there. What does it turn itself into? Particles. And particles এখানে হচ্ছে না, ওইখান থেকে particles বের হয়েছিল. So turns out it's very strange. I'll take a metal right now and I point it towards the star. ওই star থেকে কি বের হচ্ছে light. And it could be either a wave or a photon particle, right? And let's say I hold a metal out there. The light takes, let's say, 300 million years to reach me. 300 million years back, right? It knew that there'll be a what here it interacts with a metal. And what does it release at that point? Photons. And you can actually find photons come and collide with my metal. And it's a retroactive memory when it knows before it happens. For light or for us. Yeah, it is of course confusing for us. Huh? So the thing is, the information doesn't have any speed limit. That's what basically is happening, right? It means that you can't use, let's say the information is already released, and then you in between change this information that where it comes and collides, right? It already has known that it's gonna happen. No. Yes.
Is this not like superposition?
Superposition of
Information, because it already knows before, like millions of years before.
Kind of. Yeah, I mean, the thing is that you can't change this information. And then it's not like, in between you can change the structure, it will forget that information. It already knows. And then there's a simple theory behind this. It's not some, mystery or some hack in the universe. The simple theory is that light doesn't have any time frame. Light doesn't have any time that it takes to travel. Yeah, but it has to travel. But if you are a photon, right, your life never exists. You just form and you just disappear. We must change travel time to exist for now, because if you travel at the speed of light, right, time doesn't change. So for a photon, there's no time change in there. So the photon actually knows right away the metal body. Our point of view, oh my goodness, a photon knew this. And that's because we're seeing from a very slow time frame. But I'm the photon, right? I'm going to say 300 million light years is an instant. I know right away I'm going to hit a metal. So it's not a problem. So if you see from the photon's point of view, right, it shouldn't have seen this kind of, yeah. They have mass. They don't have mass, they're momentum. It's a little strange. So their mass has a momentum. So they're the only thing that has momentum without mass.
That's the key. Before the technology, algorithm,
Objective I think you came later on. So the experiment was done to make electrons come out from a metal. And we have done this using many other ways, like electricity দিয়ে electrons কে ছাড়া যায়, আমরা heat দিয়ে electrons কে ছাড়তে পারি, it's called thermal emission. অনেকভাবে আমরা electrons কে বের করতে পারছি। And তখন যেটা বের হইছিল that electrons need what to come out from any place? Energy, right? Energy basically. But the person thought that light দিয়ে তো energy দিতে পারি. So that's when he started doing an experiment to figure out how much light is needed to remove the electrons. And while doing that experiment, দেখছি তুমি যা power দিতে থাকো, right? Crazy amounts of power দিয়ে যাও, তাও electrons বের হতে যাচ্ছে না। But the moment you change the color, suddenly electrons are coming out, which doesn't make sense, because বলা হচ্ছে তুমি 40,000 joule দিবা, electron বের হচ্ছে না, but 100 joules electron বের হয়ে যাচ্ছে। sounds contradictory, right? The reason why it never worked out, this logic, is because we considered the light to be what in this case? A wave. Waver case, yes, power means intensity. But if you consider light to be a particle, the full physics changes. If light is a particle, the energy doesn't depend on intensity. What does it depend on? Frequency. And blue light has what frequency compared to red light? Higher frequency. So blue photons are actually more watt than red photons, energetic. That's where the emission took place. And the reason emission took place is because when electrons interact with light, electrons only interact with which version of light? Yes.
Sure. But when we're using light as a wave,
why isn't it coming out? Because the electron doesn't interact. So the photons that are coming in from red light, they have what energy? Less energy for every electron. So electron ke ber korar jonno je energy dorkar ওই photon গুলোতে ছিল না। Yeah, so এখানে যে of course photon, এগুলো সব photonই ছিল। কেন photon ছিল? Because you're still interacting with what? Metal, but the photons did not have what? Yeah, তার জন্য emission হচ্ছে না। না, কিছু হচ্ছে না। So তুমি এখানে একটা হচ্ছে plastic দিয়ে দাও where there's no delocalized electrons and the outer layer has no electrons, right? Just wave বের হবে, কোনো photon দেখবে না। Wave electrons don't interact with waves. Electrons will only interact with what? Photons. So ekhane kintu the thing that the light reveals as photon property is not a light thing, it's a electron thing. The presence of electron causes light to change itself into a photon.
Also, the wave to photon transition vice versa. Does that have a baseline or source থেকে?
Source থেকে। ওই যে ওইটাই তো বললাম তো যে that's why the start থেকে যে ফোটনটা বের হচ্ছে এখন ও জানে যে মেটালে বাড়ি খাবে, তার জন্য ওইখান থেকে বের হচ্ছে। Who knows? Star. That's the property of it. For it, it's not 300 million years back. It's right now. Bolam to photons don't have any time frame. So when you put the metal there, the photon thinks it's right now. So the photon is there. So very simple example. Light it's wave or photons, right? Or photons. We don't know, because আমি যদি হচ্ছে যে এটা প্লাস্টিক দিলাম এখানে wave বাড়ি খাচ্ছে, and the moment I bring a metal here, I have photons আসতেছে, and then wave. Okay, so this photons and waves interact depending on what the target is. Okay, how do we figure it out? Oh, because when we use the wave theory, it didn't work. Wave theory কি বলে যে তুমি যদি intensity বাড়ায় দাও তাহলে কি বাড়বে? Energy. So আমি তো 40,000 energy দিলাম, কিছুই হলো না তো। তার মানে the wave theory is not working here. But the moment you take light as a photon, our theory change হয়ে যায়, our equation change হয়ে যায়. Now everything makes sense, which means that this must be what? A photon. But yeah, so some of you like one of you asked here, Jay, do we see it's a wave or a photon? No, I mean we can't see that. The only way we know it's a wave or a photon is through what? The outcome. But there's no device out there that you can see a photon moving or a wave moving. We can only know if there's a photon or a wave depending on what the outcome is going to be. Okay. Good question. Metal double slit, and you put এটা light source. A wall-এর মধ্যে হচ্ছে এরকম dots আসবে, dots with diffraction দেখবে না।
Double slit experiment কি দিয়ে করেছে?
Wave.
What was the state made of?
Oh, typically they use non-metals.
Why did they not mention that?
Because A2 you're confused. A is confusion, dot is still on photons. Now, এটা আরেকটা আছে, এটা I don't want, it's a rabbit hole, but I don't want you to go there. But just বলে রাখি that there's this called the observer, theory. Observer theory হচ্ছে when you see an electron, right, move through a gap, and it comes out as what? A particle, right? If you don't look at the electron, it turns itself into a wave. If you look at the electron, it turns itself into a particle. So the thing was, people want, I think you asked me this question the other day, যে electron কেন wave হয়ে যায়? So they actually set up a device to check that যে electron কেমনে wave হয়ে যাচ্ছে? Wave হয় না সে electron রয়ে যায়. Yeah, and then once you take the device out, right, it's a wave right now. So people say that electrons are conscious, sentient, right? No, but it's actually not that. It's something different. But the thing is that you can't observe the diffraction. If you try to observe it, it just becomes a particle. So photons have momentum without mass. There's a formula for it. They're the only things that can produce momentum without having a mass. You can find their mass using a math, because if you do lambda equals h by p and you take the wavelength of light, you will find a momentum for it. But then mass into velocity, right? The speed is speed of light. So it turns out nothing that has mass can travel at speed of light. It's the law of the universe. But photons travel at the speed of light, right? So they have momentum, but they're traveling the speed of light. So something has to be missing. What don't they have? Right. So photons can exert momentum without mass. That's what they do. No, 3 into 10 to the power 8. They have zero mass. So they have no mass. They just have momentum. I'll show you the formula. Formula is that it's HC there. P equals to h by c. So if you want to find the momentum of photon, right? Understand photon has momentum, and momentum is this. It can go to mass neither. It's energy by speed of light. That's it. Okay. So it's a unique exception that it can produce momentum without having what? Mass. It saves it, or it actually conserves it, but it's not because of that entirely.
What if it's converting energy to mass?
So that's probably not happening. You had a question?
Probably is that the speed of light considered infinite?
No.
No, as in light, because the limit is the infinite basically.
The light.
Yeah.
The
it has a speed, but that speed cannot possibly.
So light has a maximum speed, and that's 3 into 10 to the power 8, right? So at that speed, you can't have mass. That's the limit of the universe. So anything with mass can never reach that speed. Anything that has that speed can't have mass. So photons fall in that very weird Venn diagram, that they're traveling at the speed of light and they have momentum. So there has to be something that shouldn't be common for both of them, right? So it's the fact that it doesn't have mass. So that's the only way you can have both of these properties show up.
So there's nothing to multiply something with nothing.
Something with nothing. Yeah, I mean, I understand everyone's confusion. You're trying to use the classic P equals to mv. No, it doesn't work here because it doesn't have mass. You can't use that equation for photon. Photon's momentum calculation doesn't have P equals to mv. P equals to mv is for what? Matter. Photon is not a matter. Photon is basically quantum. It's like a packet of energy. So you can't apply mechanical physics laws to it. So P equals to mv doesn't work for it. It has its own formula, E by C. Yeah, the only exception. Yes. No, electromagnetic wave. Yes. Yes. Ultraviolet. $1 billion question. That's like a 1-mark question. What's it made up of? Energy is energy. It's its own thing. Yeah, it's just that it's a separate class of property of material out there. How did they know? No one knows. It's still a mystery. It's that they're aware of observation. That's it. Archimedes. Okay, so if you observe them, they just know that, and they don't show their wave properties. No.
If you don't observe, you will disappear.
Yeah. Yeah, exactly. Okay, let's move on. Our question. Quantum mechanics is like this. Okay, it's the tip of the iceberg. It's horrible. So the further you go, it just ruins your reality. Nobel Prize, $1 million, a position in Harvard. Jachao, bolo, kichao. Oh no, I was just showing that if it's a wave, right? The intensity of wave would mean more energy. But whenever light source interacts with a metal, it's a photon. So it's not a wave. So these are not waves here. These are actually photons that need to come along. So we'll find less photons are coming out. So the total energy is same, but individual photons are now more energetic, right? So fewer photons are coming out. Instead of, so if you use like, let's say smaller energy photons for the same intensity, you'll find that there are plenty of photons coming out. So none of the energy laws are broken here. At the end of the day, you'll still get 100 watts of blue light, but the photons are more energetic. So they're more bigger in size. So you'll have fewer of them show up. Yes. Yes.
Do we have anything worse than this? That's more existential case.
No, it starts with the worse and then it gets easier. Okay. Right. So any question? Any further clarification? Achha, let's move on to the next part. ওটা এই প্রবলেমটাই এক্সপ্লেইন করতে গেছিল যে when you have an electron, is it a wave or a particle? এটা হচ্ছে depends on how you measure it. So if you measure its position, you can't find its wavelength. If you find its wavelength, you can't find its position. There's like a conundrum there. So we like, you know, the two sides of it, it's both, neither or not. Like ওই জিনিসটা explain করার জন্য explain the cat theory. So the cat is alive and dead. That's the thing, right? Yeah. Okay, I'll give you a 5-minute break. Then we'll start with the math. Photon, yeah. Wait, right. So if there are no electrons out there, they don't need to be a photon. So the only thing that reveals electron, photon behavior are electrons, and only electrons are going to go to random. So whatever evidence we found of photons out there came with electron interactions. Solar panels. Solar panels are photoelectric cells. Solar panel go to power generators. Till 5:30. 30. Oh, there was an interesting question here. If I sit on a photon, can I time travel? I mean, yes. No time travel. Time doesn't exist for you. Because time doesn't pass. If you're a photon, time doesn't pass for you. So existence doesn't exist for you. Yeah, it's from photon, like a photon's point of view, it's teleportation. It doesn't really have a journey because there's no time taken for the journey. The time taken is 0.
What about S equals to B?
Speed equals to distance by time. No. Yeah, that's the time taken for us, the observer, to see it. So I'll simplify this. I'm going to get an example. So there's this theory out there that if you go close to an object with very strong gravity, time slows down. So black hole the time will start to slow down, right? Cannot. So stronger gravity restricts the passage of time. Okay, and if you enter the black hole, right, how does time pass? It doesn't pass. Why? Because inside the black hole, gravity is infinite, so time can't move. So this is one way in which you can slow down time. The other one is traveling at the speed of light. So how to time travel, right? Time travel is possible. Like we can make something right now and that can allow time travel, but it comes with a catch. So system and you probably have heard of this. So you get into a rocket, right, and you fly into space, and the rocket will have to travel around the Earth at a speed of 10% the speed of light. So we just 3 into 10 to the power 7 meter per second. Let's say we make a rocket. Where rocket at the speed of travel, time passes slowly for that rocket. The closer you get to the speed of light, the slower time becomes for you. So a rocket, the person just saw 1 hour pass by, right? When he comes back to Earth, that the rocket comes and lands back, it's been 15,000 years. Because time on Earth, right, the speed on it slow, passes faster. The faster you go, the slower time gets. And the fastest you go, time doesn't travel at all. And that's what speed, 3 into 10 to the power 8. So the closer and closer you start to get to the speed of light, the slower and slower time becomes. And if you go to the speed of light, time doesn't pass anymore, and that's what a photon can experience.
So light is immortal.
Yes, if you think it has life,
So if you move at a certain speed or even few meters per second,
you're actually time traveling.
then we are basically all that.
All the
Yeah,
time.
right. So anytime you take a plane, you actually shave off a few trillionth of a second in your life. You're a little ahead than others who are on the ground.
Or did that help you?
Sir, is time a physical factor?
Yeah, it's a quantity.
Sir, what kind of
For no, light does travel at 3 per 8. So the problem here is it's relative time bola hoy. So relative time mane hocche the person in the rocket, right? For him, the time passed normally. Yes. So you're observing that, and you saw the person was out in space for 15,000 years, but the person inside the rocket, right, just saw how much passed by 1 hour. So if you're a photon, right, the photon thinks no time passed by, but you're looking at the photon from that star, right? It took 300 million years for it to reach you. So it's a point of view thing.
Should it be a change in velocity or change in speed
Or
for that?
speed. Yeah. Relative velocity. So the other object, if it's stationary, you have to be moving at a higher speed relative to that. Okay, so direction matters. Okay, question হচ্ছে, if there's any particle that travels faster than speed of light. No, mathematically possible, but we haven't found any. So mathematically impossible. There's actually a possibility that you can travel faster than the speed of light, but never at the speed of light. Okay, so but ওটা cross করতে তো হবে. So cross করা তো সম্ভব না. That's why we can't get there. So for the red light, the waves are actually photons on waves, but just fewer photons and less energy. Yes, for the red, it's still photons. I'll make this change here. Red light is still photons, but what photons? Less energetic photons. No break now. I'm to start করব. So these are photons as well. Less energy photons. Next go Tuesday morning. I think your schools are closed. It's closed right now, right? So I'll take it in the morning. Why hasn't anyone tried the rocket thing to see if time travel is possible? It is proven. There are spaceship to outer space. When they come back, their watches are different time than on Earth, and they use atomic watches. They are perfect. Ogular time change. So it has been proven. There's nothing wrong
It
there.
only go forward in time, not back.
Yeah. So the thing that we can go back in time, absolutely impossible. Okay, you can only go forward in time.
I can't forward to make it here now.
No.
It's just that you see the light far away. Maybe let's say you went back 70 light years. That means that
You are seeing the past.
yeah, we're just simply seeing the past and I come back and see the same.
No.
No.
So let's put this in context. So let's say there's a rocket that leaves Earth, right? And it's the year 2025, let's say, and the rocket goes into space, goes 70 light years away. And from that point, when the person in the rocket looks back at Earth, right, he's seen Earth 70 years in the past. That is a different mechanism to what we're doing. Our mechanism is you're not going far. You're very close to the Earth, but going very fast. That will cause you to go, or your time to travel or pass slowly. So the Earth's time will pass faster. And when you come back to the Earth, right, come back to the speed of Earth, you'll find that time is different on Earth than you. And your time has passed very slowly, and the time on Earth has passed very fast. And the other one that you said, that's like what happens right now. So when you're looking at galaxies, yeah, right. This one is the one you said is actually a delay in communication. So if you look at stars right now, none of the stars are out there. The stars that we see in the night sky, 90% of them don't exist anymore. You're seeing them where? In the past, right? Because they're 10 billion light years away. Light takes 10 million years to reach us, right? Right now, that star's not there, but you still get to see it. Why? Because light takes a long time to reach us, right? So you're essentially looking into the past.
I've also seen another graph and they show the information that's distance, but the distance is time. So what this is faster you go, the longer time. When a person is at a constant speed, the same is very good. They say that you travel like a set distance. But a person that speeds up doesn't not use an example really fast. It like goes a bit longer, like you travel more distance each time. And then when you come back, you travel more distance, so you experience I've seen that.
Oh, so the x-axis is time.
Yeah, x-axis is time. That's the distance.
On the y-axis.
It's weird because this is speed, but it's not speed. And what it is, it's faster you go, the curve goes higher.
Right.
And then compared to a person who's going constant speed, which is like this time.
Right.
And when you come back, you are like at a higher.
Oh, so you come back at a position higher. So you're further forward in time. Oh, right. Yeah, that's the reason why the Earth will be 15,000 times in the future.
I don't get why, because I mean I understand very fast, but you have the constant speed of light.
No, so the thing is, the effects of relativity start to show up not at the speed of light, close to the speed of light. So the closer and closer you get to the speed of light, the more prominent the effect becomes. So like at 1% speed of light, the effects are very minimal. At 10% speed of light, they are quite observable. At 99.9% speed of light, you can almost slow down time entirely.
So if we set out from Earth and then to a distance of 70 light, and we look back at it, what do you think?
How fast did it take for you to get there? Speed of light. So 70 years, and you see back in the past, you will see the present. When the day you left, because light traveled with you. So when you go to that point and you see the light there, it's a light that was released the day you left that place.
It's possible to see myself apart from
No, then you have to be a little faster. This is not a little faster, same speed, right?
it. Say faster than speed of light.
No, then we can't go there, right?
You got the speed of light,
No. So basically, he's saying that you start off with a rocket at the speed of light, and you look back on Earth. What do you see? Yeah, I mean, let's say from his point of view, just a little slightly less than the speed of light, right? So by the time you reach that place, right, you see light is with you, right? So you'll basically see the present when you left by the time you reach there, because the light traveled with you, right? So you're just looking at the present right now.
So my rocket takes off and I see myself double with that.
No, you just see what happened the day you left.
So it's like a slideshow.
Slideshow? No.
You remember our yes, the other two.
Screen recorder. What are you talking about?
It's like you're recording the last second after they like that.
Oh, acha. On a video. Oh, yes. Right, let's move on. So let's look into the math of this.
Recording in progress.
আচ্ছা একটু এদিকে let's observe this. So এটা হচ্ছে উপরে যা হলো এটা হচ্ছে note. See if you have understood what happened. In the experiment, light sources used to provide energy to remove electrons from zinc plate. So that's the main aim, okay? We want to provide energy to remove electrons. And what did we use for our energy source here? Light. We use red light of 10 watt power. It is observed that no electron emission takes place. The energy is provided, but still emission does not take place, no matter how long we wait and allow it to build up. এই জিনিসটা to explain করে, it's a concept that is a wave property. So allow it to build up. What does that mean? It means that according to wave theory, and listen carefully, আমাদের একটা 6-mark question আসে where you need to give differences between particle and waves. So according to wave theory, there's something called the build-up process. মানে কি, you take a torch, you point a torch at a place on a paper. As you keep pointing the torchlight there and keep waiting, that place on the paper will start to what? Heat up, and it will start to build up what? Energy. But doesn't that mean that at a point the electron will have enough energy to come out? Because let's say we wait for 10 years at the light source, energy build up হচ্ছে. At the point the electron should have enough energy, right? তাও emission হয় না কেন? Yeah, because it's a wave that's coming in. It has to be a watt for the electron to go out, a photon, right? So that happens here. So আমরা দেখছি যে if we are providing the wrong energy, but in the form of wave, it can take 10 years, your electron will still not come out. The metal will melt and turn into a liquid, maybe even a gas. The electron বের হবে না. Why? Because an electron will never interact with what? A wave. Okay? So this build-up process is a what property? Wave behavior. Yes? Metal মধ্যে photons. Yes. Right. So we'll see. It's a good point you raise. এটা একটা পরে একটা property আছে. One photon only will ever interact with one electron. They can't stack. It's just one-to-one interaction. So when an electron is interacting with a photon at a time, one electron will only capture one photon. If that one photon has enough energy, things happen. If that one photon doesn't have energy, things don't happen. It's not possible for an electron to interact with two photons simultaneously. It's not possible. So you can't stack. Because, you might think that, let's say, multiple photons start to move in, right? That never happens. So build-up process is nothing that's not possible with particles. It's only possible with waves. Right. The next one is when we use the red light of 400 on a much higher power. The magnitude is much higher, yet no emission takes place. This energy is easily capable of removing electrons from any other setup, but এখানে হয় না from a metallic surface. So এখানে কেন হচ্ছে না? Because it's very stubborn. The electron will only interact with what? A photon. And if the photon has the right amount of energy, then only it interacts. Okay? If the energy of the photon is more than the electron energy, then emission takes place. And that extra energy becomes the energy of the electron. So the electron flies with Ke. Okay. We now use a blue light of 10 watt. এখন এই যে এই part important. This is the same initial power but higher frequency. We now notice that emission takes place. This is odd since we are still providing what power? Same power. So you're just changing the color and now emission is taking place. What could be the reason? So we try the same with blue light with much lower power. Emission still takes place. But now it shows that the power is not the factor. What was the actual deciding factor? Frequency, right? What happened here is the evidence of the particle nature of wave. This is because when waves are considered to be particles, they have energy relationship E equals to hf, where frequency is responsible for the amount of energy. Since frequency is determinant factor here, it shows that light is behaving as a particle. কারণ আমার এখানে যদি wave behavior হতো, the frequency had no role to play. What had a role to play? Intensity. But in this observation, what plays a role? Frequency. And frequency can only play a role if your light is behaving as what? A particle. Okay? So I'll show you another thing right now. No. 12-mark question মানে পুরো question. Single সবচেয়ে বেশি question আসে 6 marks. ওইটা হচ্ছে যে এটা. I'll be explaining that in a minute. Had differences, right? আচ্ছা একটু এদিকে দেখো আজকে এটা just discuss করবো next as I'll give you time to write this down. It's a very important thing I'm going to show you right now, which is wave or particle কে differentiate করা. So what would a wave do and what would have you observed if it was a wave and what do you observe if it's a particle? আমরা জিনিসটা কেমনে ডিজাইন করি in our syllabus is that we will first assume, listen carefully, we'll first assume that wave আসতেছে আর wave যদি হয়ে থাকতো what would the outcome be, and then we see particle হয়ে থাকলে what are the outcome, and then we observe the photoelectric effect and we found that all the outcome matches what? Particle, and that confirms that it's a particle. Do you get my point? It's not the photoelectric effect থেকে we decided it's a particle. Particle এর কিছু properties already exist করতো, ওগুলা just এই experiment কি হচ্ছে reveal হচ্ছে. So the first property of a wave is যেটা এইমাত্র দেখালাম, it's called the build-up process. So what's the build-up process? Build-up process tells you that if you have an electron here and you have waves coming in, right? So there are waves coming in. The waves will interact with the electron, and if you give enough time, enough energy will show up here, and the electron will eventually have enough energy to what? Emit. Which means, according to wave theory, emission should take place not at a particular frequency, at a particular time and intensity, but time. Because if I give enough time, shouldn't the buildup eventually take place? That's what should have happened. But we notice that particle behavior, the emission, this is very important, is instant. Mane hocche what doesn't take place? Any buildup doesn't take place. How does that work? So look at this. Let's say you have electron here and a electroner energy দরকার for emission. Red photon আসলো, red photon energy একটু কম, এটা energy দরকার হচ্ছে 10 joules, right? 10 joules. And this photon brings in 4 joules. This 4 joules will come here of the photon, interact with this electron here, and will emission take place? No, why not? Yeah, because it doesn't have enough energy, so emission doesn't take place. But the moment, this part is important, the moment you provide the right energy, let's say the moment you provide something with 12 joules, as the photon comes and interacts with this, emission ki hobe? Yes, because you're providing the right amount of energy, in fact more. The emission to hobe. Will the emission take time or is it going to happen right away? Right away. So with particle behavior, emission takes place right away, and if emission doesn't take place, it never takes place. But with wave property, emission will one day eventually have to take place. Now tell me something. আমরা যখন এই photoelectric effect experiment করলাম, right? Did waiting help? No, right? But the moment we provided right color, emission key time লাগছে না instant. So 1 point for particle behavior, 1 point not for wave behavior. Okay, let's look at the second one. The second idea out there is that the energy of a wave depends on the what of the wave, intensity, and the energy of a photon depends on what? Frequency, right? And this one is very well observed, that আমরা যদি হচ্ছে আমার intensity বাড়াই দেই of my light, right? I can go to 400,000 and what number you can imagine, emission কি হবে? No, which shows that intensity has no role to play. But in this particular scenario, it doesn't matter what intensity your light is. If your light has the right energy, which means the right what? Frequency, what happens? Emission takes place. So this shows that this emission that took place here is not dependent on the watt of the light, the intensity, but rather the watt of the light, the frequency, which is a what behavior? Particle or wave behavior? Particle behavior. Because wave theory te ki bole? Red light, blue light. Which one is more energetic? According to wave theory, red light versus blue light, which one is more energetic? Neither or both. It depends on what power they have, what intensity they are. So this is a very simple question. edX MCQ there. A red color lamp and a blue color lamp. Which one provides more energy? A red color lamp. Oh, sorry, I forgot to mention something. Red color 100 watt lamp and a blue color 100 watt lamp. Which one gives you more energy? Same, right? Which photon gives you more energy? Yes. Okay, so যদি এটা particle হয়ে যায়, the blue is actually giving you more energy. But if you look at the wave behavior, both of them must be giving you what energy? Same. Okay, so এখানে আমরা intensity বাড়ায় দিচ্ছি. Yes, the total energy is increasing, but individual photons এর কিন্তু energy increase হচ্ছে না। আর এইটাতে যেটা হচ্ছে that the energy depends only on the watt of the light. the frequency of the light. It doesn't matter what intensity you have. Okay. Acha, what's the third property that differentiates between these two? So the third one is it's build-up moton. The third property tells you that waves can come from multiple directions and give what to your photon? Energy. Because waves যদি হয়ে থাকে stack হয়. Stack মানে বুঝছো তোমরা? Build up হয়. And তাহলে enough energy বের হবে and it gets emitted, right? But according to particle behavior, one photon can only interact with what? One electron. And this is known as the one-to-one interaction. A one-to-one interaction key restrict করে build up. When you build up possible, wouldn't it be possible that I can use like a low energy photon, but many photons come and give me the energy? সেটা হয় না. So you always need the minimum amount out there. So এটাকে বলা হয় one-to-one interaction. Or এটাকে বলা হয় many-to-one interaction. We have found that many-to-one interaction হয় না. So once we look at all the outcome of the photoelectric effect, we find that all of them point towards which behavior? The particle behavior. And that's how you conclude that light is a photon or a particle in this scenario, not a wave. So I'm the question for it 6 marks, give evidences of particle behavior of light in photoelectric effect. যখন evidence দিবা, you have to give evidence for particle behavior and also counter the what behavior? Wave behavior. Yeah, right. Photons, right? Exactly, show photons. No. These are photons. A behavior show for it, and it's a wave.
And the wave is general.
Yeah, it's generalized. Electromagnetic waves. Why?
Why not?
I mean, these are elementary things. It doesn't need a scientist to understand this.
You do something.
Oh yeah, I do enjoy it. But as a hobby, not as a profession. Right. Because if you go and talk to a scientist who studies quantum physics, is miserable. Okay, so the answerটা হচ্ছে দুভাবে দেখে তোমাদেরকে একটা তো হচ্ছে I made it this way so that's easy for you to picture, but exam এটা লিখতে পারবে না obviously. So exam যেটা লিখতে হবে is going to be this. In theory দেওয়ার কথা, it should make the life for the examiner easier, right? You draw pictures and show what the answer is. Realistic is 3 spheres of 3 different. I'm used to it. I mean, yeah, I mean, art classes, you can't force art onto someone. So I know art classes exist, which is good. I mean, they want like parts of the coloring, but as a like an adult going to an art class, I don't think that works. No, I just with art, I think it's the more you draw, the better you get. So I just drew a lot. That's what I did.
What started it?
Boredom.
That's a good book then.
My notebooks are just pictures.
You should upload your notebooks.
Right, so this is it. It to copy connect a page. I'll tell you page number. Page at the page where it says wave particle duality. A shorter version at least. It's easy to remember. That's why. Okay. Page. There's a page that says wave particle duality. Page number গুলো মনে আসে নাই। No, wait, এটা থাকার কথা নাই। Enter page number আসে নাই। So there's a page that says wave particle duality, the de Broglie wavelength. ওটার পাশের পেজে।
Who's the guy who discovered all this?
It's a collective effort. That guy who did the ultraviolet catastrophe, or নাম কেউ মনে রাখেন না, I forgot his name. It's a very complicated name. And then there was, it should be French or something. Then De Broglie is the one who, yeah, and then Einstein is the one who came up with the E equals to hf. And later on, things were ruined by Schrodinger and Heisenberg.
Why?
Because they made it into a probability. Because before this, physics was certainty, then it became uncertainty.
Because for P3 plus one. So did you play Wukong next?
Yeah, it's just ride a horse on Red Dead.
You finish the game. But how far?
I just roam around. I started and just started roaming around.
You play this one?
No, I don't do stories.
You never finished?
No, well, not now. ছোটবেলায় করতাম, and now I don't have the patience. আগে তো I used to go for 100%. You know, like everything, every quest out there. But now,
You did all the cycles. Which you
Grand Theft Auto করতাম.
managed for
Four.
how? It
There-
took me 3 months to do that.
Yeah, it took me a year. It's not like I did it in a day or something.
Didn't the commission? Which experience?
Yeah.
Do you plan it? Why? It's like a game of the game of the game of the best.
Which is three.
3, only second most overrated game. You have to.
That's how it's see.
Whatever last one is.
Yeah, I played it briefly, like
Whatever.
saved file like that.
Whatever.
One. Yeah, it was good.
Left for dead. Devil May Cry.
Hmm.
Oh,
3, 4,
are you at Final Fantasy?
7, 8,
This 7.
PlayStation 1.
Or this is 17 of them.
So একদম শুরু হলো।
Resident Evil.
Yes, 5.
Five.
The co-player one. So এই চ্যাপ্টার থেকে মোস্টলি ম্যাথ আসে, lot of math. So এই ম্যাথের equations গুলো I'll establish next class. So today just the theory part. Theoryটা, by the way, this is the answer you write in the exam. Next class আবার discuss করবো. I've just given a smaller version here for you to remember easily. But লিখতে গেলে এটা লিখতে হবে because it's like the detailed version. Okay. In the morning. Are your schools closed right now? No? When does it close? Your exams are over. Marks give no. I'll do that right. Did you collect your paper?
Recording stopped.